In this video, we're going to work on stoichiometry problems associated with limiting and excess reactants. So, in this problem, we have 5 moles of N2 reacting with 9 moles of H2, and we know that 85 grams of ammonia are produced. How can we calculate the percent yield for this reaction? Now, the first thing we need to do is write a balanced reaction. So, nitrogen gas reacts with hydrogen gas to produce NH3. Now we have 2 nitrogen atoms on the left side, so we need to put a 2 in front of NH3. And since we now have 6 hydrogen atoms on the right side, we need a 3 in front of H2. So now it's balanced. Now whenever you're given the quantity of both reactants, you need to determine which reactant is limiting and which one is excess. The limiting reactant is the one that runs out first. So therefore, the amount of product that can be produced is based on the limiting reactant. The excess reactant doesn't really run out. There's some that remains after the reaction. Not all of it reacts. So we have 5 moles of N2 and 9 moles of H2. Which one is the limiting reactant? Is it N2 or is it H2? Is it the one with less moles or the one with more moles? You can't just look at moles and determine which one is the limiting reactant. What you need to do is find out which one has the lowest mole per coefficient ratio. Divide the moles of each substance by their respective coefficients. So the coefficient for N2 in the balanced reaction is this number, it's a 1. And for H2, it's 3. So N2 has a mole per coefficient ratio of 5. H2, it's 3. So because H2 has a smaller mole per coefficient ratio, it's the limiting reactant. If H2 is the limiting reactant, that means that the other one, N2, is the excess reactant. The limiting reactant is always going to give you a smaller theoretical yield. So that's another way you could find the limiting reactant. You can take the amount of reactants for each reactant, convert it to the grams of product. Whichever reactant gives you the smaller amount of product is the limiting reactant. The theoretical yield is the maximum amount of product that you can get in a reaction. In order to find the percent yield, we need to take the actual yield divided by the theoretical yield and multiply it by 100%. The actual yield is what you actually obtain in a reaction. In this case, the actual yield is the 85 grams of ammonia. So that's how much ammonia was actually collected in this reaction. So we need to find a theoretical yield. So let's take the 9 moles of H2 and let's convert it to the grams of NH3. And at the same time, let's convert 5 moles of N2 and also convert it to the grams of NH3. So if we start with 9 moles of H2, we need to convert or change the substance from H2 to NH3. The only way to do that is to use the molar ratio, which is 3 to 2 for these two. So for every 3 moles of H2 that reacts, 2 moles of NH3 are produced. So these units cancel. And now let's convert moles into grams. The molar mass for NH3 is about 17. It's 14 for N, 1 for hydrogen, and there's 3 of them. So it's 17 grams per 1 mole. So the unit moles of NH3 cancel. So it's going to be 9 divided by 3 times 2 times 17. And so you should get 102 grams of NH3. So what this means is that if all of the 9 moles of hydrogen gas reacts, 102 grams of NH3 can be produced. That's the maximum amount of ammonia that can be produced in this reaction. Now, what about 5 moles of N2? Let's say if all 5 moles of N2 reacts, how many grams of ammonia can theoretically be produced? So the molar ratio between N2 and NH3, it's a 1 to 2 ratio. So whenever 1 mole of N2 reacts, 2 moles of NH3 will be produced. Now the molar mass of NH3 is going to be the same. It's still 17. And so it's going to be 5 times 2, which is 10, times 17, and that's 170. So notice that the limiting reactant will always generate the smaller theoretical yield. The excess reactant will produce a greater theoretical yield. So by the time 102 grams of ammonia are formed, all of the hydrogen gas has been reacted. Now, if there's no more hydrogen gas left over in the reaction comes to a stop. So that's why the excess reactant will never give you the correct theoretical yield. And now that we have the theoretical yield, we can calculate the actual yield. Well, not the actual yield, but I meant to say the percent yield. The percent yield is equal to the actual yield, which we know it's 85, divided by the theoretical yield, which is 102, times 100%. And so the percent yield for this reaction is 83.3%. Now sometimes you may need to calculate the amount of excess reactant that remains. So let's assume this reaction goes to completion, and let's say all of the hydrogen gas reacts. How many moles of N2 will be left over after the reaction? How can you find the amount of excess reactant that remains? So here's what you need to do. If you want to find out how much remains, you need to find the difference between how much you began, or the total amount of N2, that's how much you started with, minus the amount that reacts. So let's say if initially you have 10 moles of N2 gas before the reaction, and let's say only 7 moles reacts. That means that there's going to be 3 moles of N2 gas left over. Now we have the total. Before the reaction, we had 5 moles of N2. We need to use stoichiometry to find out how much reacts. Once we get that number, we're going to subtract 5 by that number, and then we can find out how much remains. To find out how much N2 reacts, start with the limiting reactant H2 and convert it to N2. It could be a gram to gram conversion or a mole to mole conversion. Since we have the moles of N2 and H2, in this problem we're going to do a mole to mole conversion. So let's start with the 9 moles of H2. We're going to see how many moles of N2 will completely react with 9 moles of H2. The molar ratio between these two is 1 to 3. So for every 3 moles of hydrogen gas that reacts, 1 mole of N2 will react with it. So 9 divided by 3 is 3. So therefore 3 moles of nitrogen gas is actually consumed in this reaction. That's how much actually reacts. So we have a total of 5 moles of N2. 3 of them reacts. That means that there's 2 moles of N2 remaining. Now if you want to, you can convert this number into grams. The molar mass for N2 is 28 grams per mole. So 2 moles corresponds to 56 grams. So you could say that 56 grams of N2 remains, or 2 moles of N2 remains. Now let's try this problem. Feel free to pause the video as you work through this example, and then unpause it to see if you have the right answer. Now we have 20 grams of propane, and it's mixed with 60 grams of oxygen gas. Our goal is to find out how many grams of CO2 should we expect to collect if the process is 80% efficient. So basically, this problem is telling you that the percent yield is 80%, and they want you to find the actual yield, the amount of CO2 that we expect to collect in this reaction. In addition, find the grams of the excess reactant that remains. So the first thing we need to do is write a balanced reaction. So we have propane C3H8. It reacts with oxygen gas, and it's going to produce carbon dioxide. And since it's a combustion reaction, we know that water is going to be produced as well. Whenever you wish to balance a combustion reaction, you want to do it in a certain order. Balance the carbon atoms first. Notice that we have 3 carbon atoms on the left side, so we need to put a 3 in front of CO2. And we have 8 hydrogen atoms on the left. 8 divided by 2 is 4. So let's put a 4 in front of H2O. Now, how many oxygen atoms do we have on the right side in total? 3 times 2 is 6. 4 times 1 is 4. So we have a total of 10 oxygen atoms on the right side. 10 divided by 2 is 5. So we need to put a 5 in front of O2. Now the combustion reaction is balanced. So what is our next step? We have 20 grams of propane and 60 grams of oxygen. What should we do next? Now we need to identify the limiting reactant. And there's 2 ways we can do it. We can convert the grams of propane and the grams of O2 separately into moles, and then divide by the coefficient to see which one has the lowest mole per coefficient ratio. And we could find the limiting reactant that way. And then once we have the limiting reactant, we can convert it to the grams of product to get the theoretical yield. Or we could convert the grams of each reactant to the grams of product, and the theoretical yield is simply going to be the smaller of the 2. So let's do it this way for this particular example. So let's start with 20 grams of propane. So here's the outline of what we need to do a gram to gram conversion. We need to use the molar mass to convert the grams of propane to the moles of C3H8. And next, we need to use the molar ratio to convert from moles of C3H8 to the moles of CO2. And then we could use the molar mass of CO2 to convert from moles to grams. So what is the molar mass of C3H8? Carbon has an atomic mass of 12, and for hydrogen it's 1, but times 8. 3 times 12 is 36, plus 8, that's 44. So 1 mole of propane has a mass of 44 grams. So the unit grams of propane cancel. Now we need to use the molar ratio. The molar ratio between C3H8 and CO2, it's 1 to 3. So for every 1 mole of C3H8 that reacts, 3 moles of carbon dioxide are produced. Now our last step is to convert from moles of CO2 to grams of CO2. So we need the molar mass of CO2. So it's 12 for carbon, 16 for oxygen times 2, since we have 2 oxygen atoms in CO2. 16 times 2 is 32 plus 12, so that's 44. So there's going to be 44 grams of CO2 per 1 mole of CO2. So the unit moles of C3H8 will cancel, and the same is true for moles of CO2. So now we could do the math. So it's going to be 20 divided by 44 times 3 times 44. Well, I guess the 44 is canceled, so it's simply 20 times 3. So if all of the 20 grams of propane reacts, 60 grams of CO2 can be produced from it. Now let's start with the 60 grams of oxygen gas. Let's see how many grams of CO2 can be produced if all of the 60 grams of oxygen gas reacts. So let's convert it to moles. The molar mass for O2 is going to be 16 times 2, which is 32. So there's 32 grams per 1 mole. Now we need to use the molar ratio. The molar ratio between O2 and CO2 is 5 to 3. For every 5 moles of O2 that reacts, 3 moles of CO2 will be produced. So grams of O2 will cancel, and moles of O2 cancel. Now the next part is going to be the same. That's the molar mass of CO2. So these units will cancel. Now let's do the math. So it's 60 divided by 32 times 3 divided by 5 times 44. And you should get 49.5 grams of O2. I mean, not of O2, but 49.5 grams of CO2. So if all of the 60 grams of O2 reacts, 49.5 grams of CO2 will be produced. Since 49.5 is less than 60, the 49.5 is the correct theoretical yield, which means that O2 is the limiting reactant. Remember, the limiting reactant will always generate a smaller amount of product. The excess reactant will give you a larger value, which will not be the right answer. So now that we have the theoretical yield, we can calculate the actual yield. Now, if you have a reaction that is 100% efficient, that means that you can get the most that you can possibly get in a reaction, which is the theoretical yield. So if this reaction was 100% efficient, we should expect to collect 49.5 grams of CO2. But it's not 100% efficient. It's not perfect. It's 80% efficient. So we should expect to collect 80% of the theoretical yield. So what is 80% of 49.5? To find it, multiply 80% as a decimal, which is 0.8, by 49.5. To convert a percentage into a decimal, divide by 100. 80 divided by 100 is 0.8. So 80% of 49.5 is 39.6. So this is how many grams of CO2 that we should expect to collect if it's 80% efficient. So the actual yield for this reaction is 39.6 grams of CO2. Now I know some of you out there prefer to use the equation to calculate the actual yield. So the equation is the percent yield is equal to the actual yield divided by the theoretical yield times 100%. So the percent yield is 80. The actual yield we're looking for, the theoretical yield is 49.5 times 100%. So the first thing we should do is divide by 100, or simply multiply both sides by 1 over 100. So 100 will cancel on the right side. 80 divided by 100 will give us this number, which is 0.8. So what we now have is 0.8 is equal to actual divided by 49.5. So if we cross multiply, 1 times A equals A, and 0.8 times 49.5, that will give us the actual yield of 39.6. So if you prefer to use the equation or just realize that you're looking for 80% of the theoretical yield, both cases you will get the right answer. Now let's calculate the amount of excess reactant that remains. In order to do that, we need to start with the quantity of the limiting reactant and convert it to the excess reactant. Since we have the grams of both reactant, we're going to do a gram to gram conversion. So let's start with the 60 grams of oxygen gas. And let's convert it to the grams of propane. So we know the molar mass of O2 is 32. And the molar ratio between O2 and C3H8, it's a 5-to-1 ratio. So for every 5 moles of O2 that reacts, 1 mole of C3H8 will react with it. Now let's convert propane into grams. We already know the molar mass of C3H8. It's 44 grams per mole. So now let's do the math. 60 divided by 32 divided by 5 times 44 is 16.5. So 16.5 grams of CO2 actually reacts in a reaction. So it reacts with the 60 grams of O2. So how much is left over? The total, or the original, that we have is not 60, but this number, 20. So we started with 20 grams of CO2, and out of the 20 grams, only 16.5 reacted. So the amount that's left over is 3.5. So this is the amount of the excess reactant that remains.